Good evening and welcome. I am indeed Frances Hellman, Dean of Mathematical and Physical Sciences in the College of Letters and Science at UC Berkeley. I'm also a professor of physics. This is the last in our series of virtual basic science events, and it's been such a pleasure for me and Mike Bochin, the Dean of Biological Sciences, to share some of the amazing work being done by our faculty and students. I'm happy to say that we're in the midst of putting together another series of these talks, which will start in late January. So you should go ahead and put in the chat window if there are any fields or topics that you'd like us to cover. We'd be happy to consider those. Um, this evening, we get to talk about one of the hottest topics in science and technology, which we are calling the second quantum revolution. You may not know this, but Berkeley, with its many strengths in physics, engineering, chemistry, and the Lawrence Berkeley National Lab as well, is a leader in this field. Tonight's group of faculty are all part of a new center funded by the National Science Foundation called the Quantum Leap Challenge Institute. This new institute is part of the federal government's effort to speed up the development of quantum computers by advancing quantum science and engineering and training a future workforce to build and use quantum computers. Just as a note, there is also something called the Quantum Accelerator, which is based up at the Berkeley National Lab, which is actually also led by one of our physics faculty members. So the foundational work that's being done at Berkeley that you're going to hear about today is incredibly important to this sort of new approach to understanding quantum mechanics. And of course, we are also very actively engaged in educating the next generation of scientists who will pave the way in the technological advances and engineering hurdles that surround quantum computation. This evening, we're going to hear from four truly fantastic scientists, plus our moderator, who is also a fantastic scientist, who are making this leap by developing new models, new understanding, and new technologies that will help researchers around the world who are working together to deepen our understanding of quantum mechanics. So our moderator this evening is Dan Stamper-Kurn, who's been a colleague of mine for many years now. He's a professor in the Department of Physics. Dan is the director of the new Quantum Leap Challenge Institute. He's an experimental physicist and part of the UC Berkeley Ultra Cold Atomic Physics Group that researches ultra cold atoms, ultra cold molecules, and light, photons, to construct novel quantum mechanical systems. They use these systems to study fundamental quantum science with applications towards chemistry, condensed matter physics, many body physics, material science, quantum information science, quantum and precision measurement, and quantum optics. So it's with great pleasure I hand the stage over to Dan.
Great, thank you, Francis. It's a real pleasure to play a role in today's events. Francis, as you mentioned, I'm an experimental physicist, and I build a complicated experimental apparatus in which we cool matter down to extremely low temperature. In fact, probably the lowest temperature of anything in the universe. And then we study what it does. And what it does is quantum mechanics, plain and simple. And so my group and I have been studying quantum mechanics for many years, in my entire career, for example. But as an experimentalist, in particular, you end up being finding yourself most productive when you look very closely at one specific thing and one specific system, often very microscopically. The topic of quantum information science, which is kind of the center of today's forum, is exciting for me because it gives me license to think about the implication of my own work in a much broader context, and also thinking about applications on a much wider scale than maybe I had thought, just based on what happens in my own lab. Being more involved now in quantum information science and now directing this center has also allowed me to connect deeply with a very wide range of researchers, such as some of the ones that we've assembled here. The next 40 minutes or so will be dedicated to a discussion. I'll have each of the four panelists that we've assembled for this event take some time to introduce themselves, give us a brief description of their area of research, let us know what really motivates them, what's a big scientific question that they're pursuing. The panelists that we'll hear from tonight are Hartmut Häffner, Birgitta Whaley, Lin, and Boubacar Kanté. So each of them will present in turn, and then I'll ask them a few questions, maybe to kind of to pull them in a more general perspective. and then we'll move on to the next panelist. I encourage you to the audience to ask questions along the way. I also encourage the audience not to give up if they hear the word quantum so many times that they can't really follow it anymore. This is a wide and also somewhat difficult topic, and you'll find, I think, that we return to some discussions that are probably yet again accessible to everybody in just a few minutes. Do remember to insert questions in the chat if you wish, and I will try to get to those questions if I have time. And if I don't get to all of you, then please find a way to ask those questions after the fact. Okay, so let me start by introducing our first panelist, which is Hartmut Häffner. Hartmut Häffner is a professor in the Department of Physics, also a member of the Berkeley Nanosciences and Nanoengineering Institute. He leads the ion trap group at UC Berkeley, which uses atomic ions that are cooled to very low temperatures so that both their internal degrees of freedom and also their center of mass motion is deeply quantum mechanical. These ion strings, these quantum ion strings, can be used to investigate quantum phenomena such as superposition and entanglement, and then to use these phenomena for quantum sensing and also quantum computing. So Hartmut, let me ask you to get started and tell us a bit about your group's research and your driving interests.
Yeah, hello. It's really a pleasure to be here and presenting or giving you some insight of what we are doing and what drives me. So, and when I think about that, actually, I think what set my mind on this was seeing my colleagues looking at single ions in their apparatus. And I was like fascinated that you can actually see these individual ions and they're so nice and crisp, and thinking about what they really are and what they can do. And at that time, quantum information wasn't thought of. And so it was kind of then how I got into quantum information, actually thinking about how we can actually compute with these ions. And so what our research group is doing is we're trying to figure out how to actually build a quantum computer. We don't necessarily want to build one. We believe that this is actually much better done in industry, who has better resources. But we want to help to pave the way and explore how to build it, what challenges there are, and hopefully solve also some of these challenges. So that's kind of the goal. And I have some slides here, and I want to share with you a few of those slides. And basically, I want to start where why do we care about quantum computations? And some or many problems, computational problems, actually require us to calculate a function. And often we need to calculate this many, many times. Suppose you want to factor a really large number, and you're just going to try what numbers you can divide that by and which of these numbers work. And that's how you factor a large number. So imagine for a moment, you could evaluate this function for all arguments at the same time, basically all at once. And that's the one essence of actually how a quantum computer works. And so a quantum computer doesn't use normal bits. It uses what we would call quantum bits. And these quantum bits, they are actually quantum mechanical objects like these trapped ions here. Here you can see a view. You can see this blue string of trapped ions, and they are held on top of this trap. It's an exploded view, so the actual ion string would be just a few hundred micron down here. But it's really nice that you can see these individual ions held there, and these individual ions, they will be the quantum bits we're going to use then, or which we are using at the moment already for quantum information processing tasks. So, but that leads to the question, what is a quantum bit and how it's encoded? So we're talking about individual ions, individual atoms would work also to some extent. The technicalities are maybe a little bit different. Professor Stamper-Kurn could tell you much more about this. But how can we encode information in an individual ion? And so what we're thinking about is, for instance, the electron being the ground state being a 0, and in an excited state as being the 1. And because these ions are quantum mechanical objects, they can be also in a superposition, basically 0 and 1, both at the same time. So this is the general idea. And that allows you now to put this quantum computer in a superposition of like being in the same state, of many states at the same time, and to compute really in parallel complicated functions. So that's the general idea here. An apparatus looks a little bit like this. So this is a picture from our lab. We have here this vacuum apparatus. There are some windows so that we can poke in with lasers, which we need to look at the ions and to actually manipulate them. And in this vacuum apparatus, we have the ions trapped, so they're in vacuum so that they don't interact with anything else, so that they remain nicely isolated and don't get perturbed by anything. And in this apparatus, we have this ion trap, and there we trap then strings of ions like here. And I mentioned this already. Each of those ions, each of those little blue dots, that's a quantum bit. And here's a simplified electronic level structure where the electron can be either in the s state, what we call the s orbital, you may remember that from your chemistry classes, or the d orbital. So, and that would be the logical 1, and this would be the logical 0. And then we can have, of course, superpositions of these states. And it's actually interesting, this blue fluorescence stems from driving this electronic transition where we excite the ion, it gets excited, it decays, and it sends out photons, and those are the photons we're collecting here. So we do the computations by applying individual laser pulses to individual ions. And the research question we are having at the moment, so this works well for short ion strings, but does it work for really long ion strings? We want to have, of course, thousands, millions of qubits. Does it work for this? And what's happening is that we accumulate more and more errors, and we need to find ways out of this. And the key word here is that we need modularization. And this is here, I want to share this. This is the vision in our field. How to do this is not to work only with a single ion string, but to break up this ion string into many little substrings, and then do the computation and actually move the ions around, like shoving the qubits or the bits through this processor and connecting the qubits when we need to connect them, but keep them isolated if we don't need them. This is the vision, and that's kind of what where our research efforts go into, studying the various problems with that. And that's basically all the slides I have. So, and I guess I'm best stop sharing at this point.
Okay, great. Thanks, Hartmut. You know, as you're showing those pictures of single ions hovering over a microfabricated chip and maybe shuttling around, you know, it looks like such an unusual hardware for a computer, that you would have single atoms or single ions, and there's many other suggestions for what quantum computing hardware should look like. You might wonder, you know, how ridiculous is this? But I reminded of the birth of the classical computer, and that in the early days of the classical computer was made up of things like television screens, bicycle wheels, and light bulbs. So, you know, where things end can be really quite different. We should be humble about what is the right technology for quantum computing. But let me ask you sort of generally about quantum science and technology. And you know, quantum mechanics itself is a pretty old topic by now, you know, already 100 years old or so. But there's now sort of this sudden explosion of interest in aspects of quantum mechanics that people are calling quantum 2.0, or perhaps the second quantum revolution. So can you say generally what this is all about? What's inspired this great interest?
Yeah, so yeah, this is actually an interesting question. So for the last century or so, we basically looked at individual quantum systems. So how does a single ion behave? How does a single electron behave? And I think we have gotten a reasonable grasp on what's going on. But the new thing is now that we experimentally are not able to control individual of these quantum systems, so a single ion, but also multiple ions, so or multiple of these objects together. And that's actually the key to understand how actually quantum information can be so powerful. So imagine you have 2 of these quantum bits. So you have 4 different possibilities. These 2 bits can be in, like 0, 0, 0, 1, 1, 0, and 1, 1. And so you have now 4 different possibilities. You can have a superposition. So that doesn't look like much, but imagine you have 50 of those. And you have 2 to the 50 different combinations, and they can't be all at the same time. And that's computationally very complex to trace. And actually, you can play this game and can say, oh, yeah, I want to understand what happens with 300 qubits. Then you would need as many numbers as there are atoms in the universe to describe just this quantum state. And that basically, I mean, you can imagine if you want to do that naively, there's no way. And so this is where the interest comes now, and it comes from the ability to control multiple like systems which are composed out of individual quantum systems. That's where the main advance was.
I see. And then what sort of makes it sensible that it's happening now? Why is 2020 the year of, among other things, the year of the second quantum revolution? Why not 1980? Why not 2060? Like, what's going on now?
Yeah, so the first time individual quantum systems have been controlled was actually only 85. So before all this Howard Schrödinger and so forth thought about, they were all Gedanken experiments. And 85, with the advent of laser cooling, people started to control really individual systems. That's really key. And then it took a while, and in the early 2000s, actually people have started to be able to control quantum systems, individual quantum systems of multiple qubits or multiple entities, and that basically create entanglement in a deterministic fashion. And so it basically slowly built up, and now we are at a phase where we can run reasonable algorithms and where people see more and more where this could go to. Before, yes, it was cool science, but people didn't really necessarily believe that it could be a big thing. But now suddenly industry is rushing into the field, and you can see that, for instance, with Google or IBM, they go into the field, they take it from the scientists, and they accelerate just progress with their fantastic resources, which we don't have at the university level. But that basically made a big step. And then, right, it goes back. Then suddenly China thinks this is a big thing, so they invest a lot. Europe goes into it, thinks it's a big thing, and then suddenly, oh, the US thinks we are behind. And so I think this is how it built. And so it
Somebody
took a while.
saw it on Facebook, and off we go. Right. So some questions are streaming in. I'll just ask one, which Alan Dean and also Thomas Schneck are asking, which is, what would it look like for a quantum algorithm to be implemented in one of the devices that you're considering using? So how do things like gates and computation, how does it actually work out?
Yeah, so you can think of actually like, let's say you wanted to invert a qubit. So you have the electron being the ground state, and you wanted to invert it. So you need to promote the electron to the excited state. And in this case, you would apply a laser pulse, which excites the electron. And the cool thing is, you can actually find out, oh, I need to apply the laser pulse for 100 nanoseconds to do this. What happens if you apply it only for 50 nanoseconds? Then you create this weird superposition of the electron being the ground state and excited state in the first state. So the algorithms are encoded in terms of laser pulses. You direct the laser at I number 1 for a certain amount of time, then you go to I number 2, then you go to I number 2 and 3 at the same time to have some conditional operations, and that's how it's built up.
Nice. Quantum laser light show. Make sure to wear your goggles. Okay, great. Thank you very much, Hartmut. Let me move on to our second panelist. Our second panelist is my colleague, Birgitta Whaley, who is a professor of chemical physics and a director of the Berkeley Quantum Information and Computation Center. Her research group works in 2 different areas. The first of these is quantum information science, including quantum computing. In this area, Professor Whaley and her group study how to run quantum algorithms, particularly on quantum computing systems that are still noisy and somewhat faulty. The second area of her research is quantum many-body systems, that is, how quantum mechanics describes the nature of real complex physical systems. And there, with her research group, she focuses on systems containing strongly correlated electrons, on small systems that are embedded within larger environments, and also on quantum effects in biological systems. So now let me allow Birgitta to take the stage and tell us about her research group's work and what's driving her research at present.
Thank you, Dan. It's a great pleasure to be here this evening and to have the opportunity to tell you a little bit about what we do and give you some sense about how exciting this field is and how it's really moving. It's even more exciting now than it was 15 years ago or 20 years ago when I started to work in it. Let me share my screen and I'll start by showing you my group here, which is my group is the people here on the left, in front of the historic Hearst Mining Building, where we actually had our first quantum information and computation center at Berkeley starting in 2003. And okay, so in my group, we basically do many different things, and everything's fine to do as long as it's quantum. That's the ground rule. And I started working in quantum computation fairly early, about 1997 or so. And it's really been an exciting journey from then to where we are today, where it's a full-blown experimental, global experimental race to build these machines that can do such wonderful things. So as Dan mentioned, I'm a theorist. And this picture may seem a little dry compared to Häffner's, Hartmut's beautiful ion traps, but this gives you an idea of the structure of how one can do computation today, which is basically in a hybrid device, because the machines that are currently being built are all, they're scaling up to, maybe we hope to get to 100 qubits within the next year or so. And they are very, they only allow, so the challenges here on the right, to summarize, we only allow, they have no error correction, and they have qubits with limited lifetimes or limited lifetimes for doing quantum gates on them. And there's a considerable amount of noise, both in the gate processes and also in the measurements. And in general, an interesting point about the difference between quantum algorithms and classical algorithms is that the quantum algorithms are often probabilistic in the sense that one has to repeat them many, many times. And so one needs to repeat these circuits many times. And so what's shown here on the left is the quantum part of this schematic of a quantum computer is the blue part here, which shows 5 quantum bits, the type all initialized beautifully in their 0 state. And these are, as time evolves and operations are made on them, one goes from left to right. And these white boxes indicate the gates, the analog of classical gates that are being made and that connect on each of these qubits, and these ones which cross 2 lines would be connecting these 2 qubits and causing to undergo some coherent quantum operation. It may be entangling them together. So the idea today is that one can do a certain limited number of these quantum operations, and then one can measure, and this red box indicates a measurement apparatus, and that measurement apparatus is something which is partly quantum because it's touching the quantum objects, but it's converting the output into classical signals. And those classical outputs, the measurements, are then put into a classical processor, a regular computer, maybe your someone's laptop or a supercomputer. And then there's some processing on this output being done, and it might be an optimization scheme, which allows then the parameters which control these different gates in this circuit to be varied so that to optimize the result of the measurements to achieve a desired outcome of a circuit. So this is the modality in which virtually everything is being done today. And the kind of problems that can be addressed with this are optimization problems, and there's a lot of problems in physics and chemistry where one wants to variationally optimize something like the energy of the system. The second type of problem is one can sample random circuits very easily this way. In other words, and this is actually what has led to the breakthrough result last year from the Google team, who basically just put in here random quantum circuits and sampled them and showed that this could be done more effectively on a quantum device than on a corresponding classical device. And they made this test with 50, I think it was 53 quantum bits, and it was just above the barrier what was possible at the time with classical computers. We're also looking nowadays, so that's what people would term quantum supremacy or quantum advantage, whichever name you prefer. And there's other areas where this quantum advantage, which is really a very powerful evidence that quantum computing is really of use, can be found. Quantum chemistry is one. There's an advantage here for studying states of molecules with strong electronic correlations, where classical methods scale exponentially. And there are many, many situations where one's trying to simulate complex quantum matter systems, or even classical matter, where the power of the quantum computer could possibly improve on classical calculations. For instance, if one has one of Hartmut's ion trap systems, it's only possible to solve for if you want to solve for the dynamics and understand how perturbations and to the system change the system in time, you really can only go to about 30 ions currently. And that's not a lot. But with a quantum simulator, quantum computing acting as a simulator, you could go to many, many more. And also, so the applications of this are really quite enormous in not only chemistry, physics, bio and geosciences, but also in aeronautics, robotics and engineering, finance and analytics. And really all of these last topics rely on, where the reason that a lot of people in finance and analytics are interested in this is in the possibility of optimization. It's really the optimization that's driving a lot of the interest in the field outside of science. So then let me also say a couple of words about applications to biosciences. So here's actually an experimental effort that I'm working on with my colleague Graham Fleming in the chemistry department, who is an expert on study of photosynthesis. And what we're doing here is we're using the tools which have been developed and really perfected in the last few years as a result of the growth of quantum information technology, as well as quantum information science. And here we're using tools of correlated photon pairs, which have been known for quite a while, but they can now be shaped and all sorts of extra things done to them. And we're using these pairs of single photons to probe the initial process of photosynthesis in this particular case, it's a purple bacterium that has this structure shown on the left here, where there are these rings which absorb light from sunlight, and then the energy is from the light is transmitted to these big circles, where it's converted into electron hole pairs, and chemistry happens, and storage of energy happens in chemical form. So what we're doing here is we're using these individual photon pairs and making correlated measurements between different detectors at this other end, and then measuring the statistics of those correlations and using those statistics to understand how the initial process of absorption of a single photon happens here. And Hartmut mentioned actually the control of individual quantum systems starting around 1985. And in 1986, there was a paper from Germany, from Hans Demotte, who showed that a photon is absorbed in single jumps in atoms. And this is something which had a long history, going back to the 1920s, when there was a big argument between Einstein and Bohr and several of the others, greats of the time, about whether events in quantum mechanics happened by chance or had to be deterministic. And even so, already even before this, Bohr had proposed the idea of quantum jumps. So so only in the 1980s, though, were these jumps seen for the first time. And now we're looking really to see whether these jumps can be seen not in individual isolated ions or atoms, but in very complex systems, in systems that actually are essential for life on Earth. So that's the far reach, this is really outer reach of quantum information today. And I think that's all I have for slides. So I'm happy to stop sharing now and maybe answer any questions that Dan has.
All right, Birgitta, terrific. Maybe I'll direct you to some questions just about like generally what quantum computing is. So can you sort of summarize briefly what is a quantum computation? How does it work? And why is it superior to classical computers?
So quantum computation requires that one has these bits which have this quantum behavior that Hartmut described, where instead of having just zeros and ones, that you can have something which is simultaneously in 0 or 1, 0 and 1, or 0 or 1, if you measure it. And that's what we call a superposition. Then we have to have the ability to have these two-level quantum systems in their superposition states interact with each other and form states that have special correlations, which we generally refer to as entanglement. And then, so then there's this aspect of doing things in parallel comes in, that you can certainly, it's true, you can explore a lot of the space of all of those quantum bits at the same time. But none of that helps you unless you have a very clever last part, which is that you choose your measurement carefully. And a lot of the really, really good quantum algorithms have very surprising last steps. And it's really the finding not only the propagation of a parallel superposition, but it's also figuring out how to extract the information at the end. Because in a sense, you only get one chance, because when you measure a quantum system, it generally collapses. Certainly if you measure, it collapses onto one of many, many possible states. And so you have to think very carefully about what measurement you're going to make, which qubits you're going to measure. And you want to do the measurement so that ideally that your answer to the computation falls out in one step. And generally it doesn't fall out in one step. It generally falls out with some probability. So that's why you then have to repeat it many, many times.
Yeah, so one of the things I'm learning from discussions with Birgitta, also with other colleagues at Berkeley, for example, Lin, who we're going to hear from in a second, Umesh Vazirani in computer science, and others, is like how subtle this new kind of computer science is, quantum computer science, where we just barely know how to get advantages for quantum computers, but what we're finding is very powerful indeed. Thank you, Birgitta. Let me move to our third panelist. This is Lin. Lin is an associate professor in the Department of Mathematics. His interests span numerical analysis, computational quantum chemistry, and computational material science and quantum computation. The research that he and his group do focuses on the development of efficient and accurate numerical methods for electronic structure calculations, which has applications in quantum chemistry, quantum physics, and understanding the properties of materials. So Lin, maybe you can tell us about the research that you and your group do and what you find interesting at present.
Sure. Thank you, Dan. So as Dan introduced, my group really focuses on the development of efficient numerical methods for quantum antibody problems. And quantum computers are very efficient methods for solving quantum antibody problems that really naturally was very interesting to me. And over the past year or so, I realized that in a broader context, which is using quantum computer to address other problems in scientific computing, is also very interesting, especially the so-called quantum numerical linear algebra. So what is quantum numerical linear algebra? Basically, if you remember, so at Berkeley, there is the introductory level course called the Math 54. And the first class is to solve the equation AX equals to B by hand. And later, you're going to use the computers to solve this for very large matrix A. And quantum numerical linear algebra says whether we can solve these equations on a quantum computer. So, but it includes more things. They're like solve eigenvalue problems, compute matrix exponentials, singular value decompositions, etc., can all actually be performed efficiently on quantum computers. And just in the past 2 or 3 years, there have been many interesting and exciting progresses along this direction, and with applications in computing problems from quantum antibody problems like ground and excited states electron structure problems to spectroscopy information like Green's functions, but also in many other areas, as Birgitta said earlier, like in biology, in finance, also so-called quantum machine learning. So today, what I want to talk about is a very specific thing that we recently worked on, is that assume there will be a day that there are like 10,000 quantum computers. We're pretty far away from that, but remember that in the 1950s, IBM predicted that the world only needs 5 classical computers, right? Now we have about 2 billion computers. So assume there will be a day that there are 10,000 quantum computers. They definitely don't look like this. What should you do to select the so-called top 500, sorry, I forgot to do this, top 500 quantum computers? So what does it mean? So we first ask the question, how do we do the job for classical supercomputers? There's actually a well-defined procedure. It is called the LINPACK benchmark. And this was what I got in June. I think the more recent one will be released very soon in November or December. Like in June, the Japanese supercomputer beat the Summit supercomputer by the US, became the #1 in the top 500 list. And the name of the computer is called Fugaku. How do we say Fugaku is better than the second Summit? It means that you run a particular package called high performance LINPACK. What it does is exactly to solve a very large or a series of very large AX equals to B problems, solve linear systems, and you reach a certain number of floating points operations per second called flops. And then Fugaku was the best, so that's the #1 computer. So this criteria has been used to define the top 500 list since the debut of the list in 1993. And what we want to do is to propose an analog of the classical LINPACK benchmark. It's called the quantum LINPACK benchmark. And Birgitta has said that last year, Google made a big splash in the news by declaring that quantum supremacy was reached. If you think that, what is supremacy? It's basically saying you can achieve a goal that a quantum computer can do and no other classical computers can outperform it. But this task does not need to be useful at all. So you can think, ultimately, we want to reach the top of the quantum Mount Everest, where the quantum computer is not only faster, but also does a useful job that the classical computers cannot do. And this point is called quantum advantage. We're climbing that, but this is going to be a pretty steep curve. And the quantum LINPACK benchmark is something along the way. And in particular, it may not be that far away from Google's quantum supremacy test. So this may be a little bit even drier, but just to get you some idea what's the basic components in this LINPACK benchmark, it addresses a very important issue that is quite thorny if you think about real applications, which is how do you get this real data into a quantum computer, especially on the so-called near-term devices. So the way we think this LINPACK benchmark is to think the other way around. That is, whether you can use some matrices that are inherently easy to generate on the quantum computer, and then you do something that is useful. for example, solving a quantum linear system or computing the thermal energy of the corresponding Hamiltonian. So this is the so-called random circuit block encoded matrix model called RACBAM. And the idea is very simple. That is, you have a certain quantum architecture, you generate some quantum gates, which are some unitary matrices, and that are easy to be generated on quantum computer. And then you take just a sub-block of this random unitary matrix, and you study this kind of random non-unitary matrix as this truncated unitary matrix from the quantum circuit. It turns out this is a very general way of representing matrices. And in fact, up to a scaling can be any matrix. But the advantage is that it is a very flexible way and fully respect the coupling map of any given near and future quantum architectures. So to give you some idea that we have tested such ideas to generate these matrices with some more advanced techniques, you can really solve linear systems on near-term quantum computers. So this data is obtained on the IBM Q machine, and this is obtained from the corresponding quantum virtual machine. These are very preliminary data, and the near-term devices are rather noisy. But the take-home message is that you do gain some accuracy, and we're in the progress of making more tests on the Google's computer.
Lynn, thank you very much. So you reminded people that if they had taken Math 54 while at Berkeley, which is our linear analysis and differential equations course, they were solving matrix equations, and now you know, maybe we find that quantum computers, that's one of the things that they can generically do very, very well. But that brings me to the topic that I'd like to ask you about, which is about education. So how, you know, we're imagining quantum science and technology sort of becoming a new industry, and then therefore needing a workforce that is trained with particular skills and particular ways of thinking and of being creative. So what kind of education should we be providing to young people, or maybe even retraining senior professionals so that they can enter into quantum science and technology?
This is a very good question. As you said, that the quantum computing is such an interdisciplinary area, and many experts from different areas, including physics, chemistry, ECS, and mathematics, are all contributing to this area. And honestly, the boundaries, the domain boundaries are often blurred. And so on the other hand, all different areas, they might want different things out of the quantum sciences. So I think to make such a distinction would really be helpful. That is why I think, for example, the Berkeley, there are already different departments are offering different aspects of quantum information to the students. For example, Birgitta has a long-running course, to mainly towards undergrad students, and in the chemistry department, although it's also cross-listed in many other departments. Umesh gives that from the EECS. And in this QLCI Institute, I also would like to collaborate with Birgitta and Umesh and get another special course offered from the math department, and cross-listed also in physics, chemistry, or EECS. I think all these complementary different perspectives, so the students can learn from different faculty members and to see what kind of things they would like to get from this. And another thing is that from the educational perspectives, I think even the disciplines I haven't mentioned before could also make significant contributions. For example, I haven't talked about material science department, But we all know that there's a very intimate connection between the quantum physics, chemistry, materials. I expect that those departments will also make very significant contributions.
Yeah, it's definitely an area where a place that is as broad and strong as Berkeley is going to be able to really define going forward how quantum 2.0 is taught to
I do think so.
students at all levels.
Yes.
Thanks so much, Lynn. Let me move to our fourth panelist, and that is Boubacar Kanté. Boubacar is an associate professor in electrical engineering and computer sciences. His group researches the area of matter wave interactions, from microwaves to optics. He's mostly known for his invention of topological light sources and lasers. And the goal of his research and that of his group is to harness the on-demand dimensionality of materials and nanomaterials in order to address global energy, defense, and health challenges. So Boubacar, maybe you can tell us about the work going on in your research group, and again, what sort of inspires you in the quantum field.
Okay, thank you, Dan, for the introduction. So thank you everyone for being here. I hope you are well. So I am actually very excited to be part of this quantum information event. And I would say that the research obsession in my group is basically to use light, so the fastest vibration of the universe, to perform better computing, better sensing, and better imaging in order to improve our lives. So, and this research involves developing more efficient and novel light sources. So that can be integrated on tiny chips. So it involves the development of photonic circuits and materials, so that can process the information encoded in light. So it also involves the development of new detectors. So basically what we are doing is that we are working to integrate light sources, light processors, and light detectors in single and tiny chips. So actually during the last few years, so we have spent quite a bit of time developing light sources. And as you just said, doing so, we invented topological lasers. So let me maybe use that to share what we have been doing on that topic. So I will share quickly my screen. So topological materials are quantum materials, that have been investigated quite a bit during the last years. And they were first developed in condensed matter physics. And topological materials are interesting because they basically show that there is a classification of materials that goes beyond the well-known Landau symmetric classification of materials. And this demonstration was originally done for condensed matter system, for fermionic systems. And what we have shown is that we can use topological principle to implement new optical devices. So here I'm showing, so this is a cartoon. I call this a topological puzzle. So it gives a new degree of freedom for kids to play, but it can be more serious than that. So here we have an insulator for light, basically a mirror, and you have another insulator here for light, another mirror. The two insulators are topologically distinct, meaning that one is like an orange and the other one is like a donut. So the orange has no hole and the donut has one. So those are said to be topologically distinct because to move from an orange to a donut, you need to punch a hole, and that's called a topological transition. So if you interface two materials like here that are topologically distinct, what happens is that you can actually guide light at the interface of the two topological materials. And what we have shown is that if you take an arbitrary closed contour between two such topological optical materials, you can actually guide light on arbitrary trajectories. And this is interesting because a closed contour like this is a cavity. So we basically created a topological cavity. So we use that to demonstrate topological lasers. So here is a sketch of a device that we fabricated. I will show what it was done. So basically, the central photonic crystal is a mirror. It's operating in a band gap. So it's the donut, and the external photonic crystal here is the orange. It is also operated in a band gap. So both are mirrors. and light can only circulate at the boundary of the two materials. And interestingly, because we developed this system by combining 3-5 semiconductors and magnetic materials, so we can actually control the direction in which light flows. So I call this the photonic quantum Hall effect. So with a magnetic field, I can control if light goes clockwise in this cavity or counterclockwise. And by coupling this cavity to a waveguide here at the bottom, so when light goes, let's say, counterclockwise, you will basically send your light to this output of your waveguide. And you can dynamically, in real time, switch your magnetic field and switch light to the other part. So this is basically a topological switch that we use here as a laser that can send light to a selected output. So this was very exciting. It was the first time that a topological laser is made, and I think it will have a lot of applications. So here is another example of a topological singularity that we use that we call exceptional points. So this sketch is a little bit complex. It's also a cartoon, but it's actually the plots correspond to actual data. So here we have two modes that disperse as a function of some parameters. And the system we are coupling are metallic nano antennas, so that support plasmonic modes. And basically, we can drive the coupled mode to reach a singularity that is called an exceptional point, where both the resonance frequency and the loss rate of the coupled system coalesce. And these singularities are known to be very, very sensitive. So if you use them as detectors, you can detect tiny, tiny quantities. So we implemented this system experimentally. We fabricated them here in the Nano Lab. And we use it as a sensor when the plasmonic system was operated around the topological singularity. We functionalized the sample with immunoglobulin G, which is the most common antibody found in human blood. And what we wanted to do is to detect that anti-mouse IgG here at very, very small concentrations. And we were able to do that at concentration up to about tenths of attomolar. So that's really, really small. And why is that important? So that is important because, for instance, when you go to your doctor, your blood is drawn, they usually don't give the result right away because you have to go home and wait for a few hours or days so that the analytes or the virus or bacteria that is in your blood can be grown to reach a quantity or a concentration that is high enough to be detected. So if we can improve the quantity, the sensor, so that we can detect smaller quantities, you will basically have to wait less time to be diagnosed. So this is really, really important. It can have a lot of implications. So of course, this system was probed with classical light. So we have ideas on how quantum light could potentially be used for similar systems. Actually, I had a discussion with Birgitta yesterday. So hopefully I will work with her in the future to implement some of those. So I will just share quickly here an image of the people actually in the group who are doing the work. So those are students and postdocs in my lab I work with very actively every day.
Thanks, Boubacar. I think everybody in the present moment is inspired by the thought that quantum devices can be used to become more sensitive biological assays and maybe to fight disease. Let me ask you a general question about, since you're a representative from the College of Engineering, an idea that's emerging within UC Berkeley and also elsewhere is to establish like a new branch of engineering that might be called quantum engineering. Mm-hmm. What is this? How would you define this discipline?
Yeah, that's an interesting question. So quantum engineering, I would say, is basically a practical approach to quantum technologies. So beyond, I would say, basic understanding, usually engineers like to understand why a concept is useful. So I teach in engineering. So usually when I start the class, one of the first questions that my student asks is, why are we learning this? Why is it useful? So probably in physics, that's not the first question because people are interested in basic principles sometimes. But in engineering, really a lot of students are driven by the practical aspects of things. So quantum engineering then will include both fundamental physics and a broad skill set that will be put together in order to meet some practical challenges. So a quantum engineer will have to be trained to use the tools and the language of quantum mechanics, but you also really need to learn tools and language from electrical engineering, from computer science, from material science, and many other disciplines. So, so the main challenge here is that for instance, in the center that you are leading, that I'm very happy to be part of. So I think it is a great opportunity for scientists actually to work together, because the multidisciplinary aspect is really key to success in these naturally multidisciplinary problems.
Right. And then how do you imagine the engineering challenges of quantum information science? What parts of them should be pursued in academia versus national labs versus industry versus elsewhere? What's your perspective on that?
So, I mean, that's also a challenging question, I would say. So I think, I mean, it should be pursued everywhere. Okay, so as I said previously, collaboration is key to success in this topic. And I would say that maybe in academia, we need to do the basic proof of principle, the basic demonstration, that those can be done in universities. And we will need maybe national labs to make mid-size or systems to start scaling basic proof that were done on campus. And then this could be done in collaboration with natural labs. Now regarding industry, so I think they have more resources to scale even further the size that will be first developed in academia and then in national labs. They can help not only invest and make milestones that will justify the investment that is made by different entities on the topic.
Right. Right. All right. Terrific. All right. Thank you very much to all the panelists. I'm going to hand the floor back now to Frances Hellman, the Dean of the Division of Mathematical and Physical Sciences. But before I do that, let me just tell you a few things about Frances. Frances is a colleague, a professor in the Department of Physics, and specifically is a condensed matter experimentalist. She studies the thermodynamic properties of novel solid materials, especially thin film, semiconducting, superconducting, and also magnetic materials. She is president-elect of the American Physical Society and a member of the American Academy of Arts and Sciences. Her work is a really great basic science story. So that in the sense that when you go study basic science, you follow where it takes you, and it might take you in some pretty unexpected directions. One of them is that Frances is now a member of the LIGO team, which is the team that uses a light interferometer to sense gravitational waves. And you might say, what does Frances have to do with gravitational waves? Well, it turns out that the materials that Frances is studying turn out to be perhaps very important coatings on the mirror surfaces that can help them get around certain noise issues. So now she's also a gravitational physicist. Anyhow, Frances, the event gravitates towards you.
Thanks, Dan. Well, that was really fun. Thank you, all of you. Thank you, Dan. Thank you, Hartmut, Birgitta, Boubacar, and Lynn for sharing with us your work and giving us this glimpse into the next frontier of quantum mechanics. You know, as Dean, without question, the most enjoyable part of my job is to listen to our faculty, interact with them, conveying their excitement about their research. It's contagious, and it's a great reminder of the excellence that exists here at Berkeley. I also want to say a special thank you to our alumni and friends for gathering and talking about the importance of basic science. This series of science talks is intended to shine a light on this type of science and to convey its importance in all of our scientific endeavors. Quantum information is really a perfect example of scientific research that is burgeoning and filled with promise. And, you know, everybody wants to know when we'll have a quantum computer. And of course, we all want to know that. But the answer isn't simple. There's a lot of promise, a lot of buzz, but it's still an area that is in desperate need of foundational research. And of course, this research is going to lead to a deepened understanding of quantum mechanics, which has fascinated scientists for 100 years. So I hope that you feel that these scientists demonstrated this excitement and its importance tonight, and hopefully that the talks gave you some insight into what all the buzz is about. So your support and your advocacy for Cal means absolutely everything to us and to the faculty, like Dan, Hartmut, Birgitta, Boubacar, and Lynn, and their incredible students. You heard from the faculty tonight, but trust me, there's a whole group of students out there that are deeply involved, and much of the work, that's their thesis work or their undergraduate work. We are very gratified for your continued interest in Berkeley, which is alma mater to many of you, and to the path-breaking work that is being done here. If there's anything you want to learn more about, or if you'd like to support our work, for which there is a deep need, please be in touch with us. We absolutely want you to be part of advancing basic science and discovery at Berkeley. So with that, happy Thanksgiving. Please stay safe and well, and fiat lux.